So I've been doing big data consulting for a while before I joined Typesafe to work on tools like Spark, and I realized pretty quickly that the tools were terrible. So I started trolling the community back in 2012 or so when I started. And back in those days, typically if you wanted to do big data science at scale, what you would typically do is create your models in Python and so forth, and then throw them over the wall to some Java developers to write MapReduce code. Which kind of sucked. And I did a talk about 3 years ago at the Northeast Scala Symposium where I argued that big data needs to be functional. And what I meant by that is that, I love what Martin and Todd said this morning about functional programming. It can be a bit religious and dogmatic at times, or at least certain people in the community. But it does give us the right abstractions for working with data and thinking of it as immutable values that we transform and so forth. And it turns out that SQL is actually a functional language of sorts, and that's always served us really well. So, first of all, you might say, well, why use the JVM? Well, I think we all know that it's a well-established platform. It does scale extremely well. There's just a lot of tools we've had for a while. Different programming languages now, like Scala and Clojure in addition to Java. Those are math libraries on the right in Scala, Algebird, and Spire that I won't really talk about. And then we've got mature development environments. And these days we've got a very mature ecosystem of tools, mostly around the Hadoop ecosystem, but not necessarily all of them, that let us approach different kinds of data problems at scale. There's just a laundry list of some of them here. We're going to talk about Spark a little bit. A predecessor to Spark that was very influential was Scalding that Twitter wrote, which sat on top of MapReduce. And that bird is actually their summing bird, which is the tool that abstract over Scalding and Storm. So mostly what I'm going to talk about is in the context of Hadoop, but it's not specific to Hadoop really, but it sort of sets the stage for what we have to do at scale. I think, actually, how many of you have actually used Hadoop before? Okay, most of you. So I'm not going to spend a lot of time talking about Hadoop because it's mostly familiar, but just to give you a sense of kind of how you would approach data science at scale. And very schematically, a Hadoop cluster looks something like this, where you have master nodes that own the jobs that you're going to run on the system. So for example, this resource manager is the current Hadoop way of managing a job that you submit. It figures out when it has resources to run your job, and it breaks it into tasks that are run on the slave nodes, and it delegates to these node managers the actual execution and monitoring of your tasks locally on each machine. And then underneath Hadoop has always been this distributed file system called HDFS, for Hadoop Distributed File System, that has its own services. The name node is the master for the whole file system. It knows all the metadata about files. And then it has data nodes that manage all the blocks that are on hard drives around the cluster. And traditionally you would write MapReduce jobs that you submit to the cluster, to the resource manager today, and they would then be scheduled and run. And that's great if you can write MapReduce code, but that's not really such an ideal scenario for a lot of people. So what is MapReduce? How does it work briefly, very conceptually? One of the examples I'm going to go through, but not actually in MapReduce, I'll talk about it in the context of Spark, is a fairly famous algorithm called the inverted index. And it's sort of what you would do as a minimal implementation for something like a search appliance or Google or whatever, which is, I have all these pages on the internet or some document repository. I want to create an index. They call it reverse index or inverted, because I'm going to find all the words in this document and build an index of word to all of the locations that word can be found. And I even want to know the counts, because obviously I'm probably more interested in documents that talk in great depth about a topic, not ones that mention it in passing. So we would like to calculate this. If you actually want to see sort of the particulars of how this works in MapReduce, I have some bonus slides at the end of the talk that I didn't want to go through now. But the idea is that I'm just going to pass it through some miracle, some cluster, and then it's going to pop out the other end. And what has to happen as a precursor step is we're going to have web crawlers that go around the internet and find all these documents and write an initial data set that has, like a two-column table, if you will, the location where it was found or some ID representing that location, and then the contents. And then once again, the inverted index that comes out the other end will be indexed by words, and then a list of places where the word is found and frequency. And just to zoom in a little bit, this is what kind of the data would look like if we were crawling Wikipedia. It might look something like this, but I don't want to belabor the point too much. And the output would, I forgot about this a bit. So anyway, getting on to the issue. The problem with MapReduce that we ran into, and the reason I was trolling it a couple of years ago, was it's actually really hard to map problems down to a low level, very coarse-grained. You have this map step that does initial processing and a reduce step that takes that temporary data and collapses it down to your final result. That, again, I skipped over the details for time. You can find them at the end of the talk if you want. And this was one of the reasons why most data scientists never bothered really learning MapReduce, because it was a waste of their time to master the arcana of such a low-level system. Instead, they would let Java experts, Java engineers worry about that. And it really actually became a subspecialty, is knowing how to write MapReduce code, how to actually use that API. So in fact, if you actually go through the Java code, it looks something like this. I know you can't read this, it's 6-point font, but it's like something like, I think even, what was it, like 80 lines of code, but it was very detailed, arcane code, the kind of stuff that you would spend hours writing, unit test thoroughly. That was another thing that was hard to do in MapReduce. Not something that you really want to do for what is conceptually a very simple algorithm. So we want to see a better way to do that. And one way is, well, can we layer some higher level abstractions on top of this to at least make it easier for people to work conceptually in like data flows or SQL? And the first one that became extremely popular was a SQL query tool that would generate MapReduce jobs for you, where you're basically using SQL as a domain-specific language for the problem. And you could write things like this, create some table, load data into it, and then write, select queries on the data. It wasn't a transactional database, what's still around, so it's not like in past tense. It was really purely for putting the queries back in SQL. It wasn't designed to do record level stuff. It was designed for table scans. I love this tool so much, even though I don't consider myself a SQL person, that I co-wrote a book on it because I wanted to make sure people knew how to use it, because it was so useful for sort of the 80-20 problem of the kind of things people did for at least basic analytics. But the problem with it was that you had to write any extensions that you might want, your so-called user-defined functions, in Java, which again brought you back to working with the engineers and figuring out how to deploy this and all this kind of stuff. You couldn't just embed a Java function or class inside your Hive query and then just have it work. You had to go through a lot of rigmarole to extend Hive. There was another tool that got popular called Pig. This was written at Yahoo, and the name was sort of an accident, and it just kind of stuck around. And the dialect is called Pig Latin. Okay. This is a data flow tool. It's designed a little better for the sort of scenario where I'm going to just walk data through a series of steps of transformation, maybe forking the data, and have two pipelines that are doing different things. This is actually basically the same thing I just showed, a simple situation where I load some data and I project out just one column, so to speak, of that data. Pig is kind of a strange language in terms of it's not familiar if you know SQL. It doesn't kind of look like Java. And it's not Turing complete, so once again, you are kind of stuck with a situation of, if I want to extend it, I have to write code in another language and link it in. Although in this case, you could use Python and Ruby even and JavaScript. If anything that could be run is in a JVM, you could actually use. You weren't just limited to Java, which was nice. But my favorite in this early stage, again around the 2012 timeframe, was a Scalding library, yes, written by Twitter. It's actually a Scala language, and I'll just show you a quick code example of this, that actually was setting on top of another nice API called Cascading, which gave you more data flow abstractions, even though it still had kind of the verbosity of pre-Java 8 Java. And by that I mean it really could have used lambdas or anonymous functions, which we now have in Java, but this was, again, several years ago. And that would abstract a lot of the hassles, a lot of the low-level details of writing MapReduce code so that you could write very high-level language kind of stuff. And this is what it looks like in Scalding. I won't go through all the details. Really, I want you to get a sense of how concise this code is, that I've suddenly taken a software engineering problem and turned it into a script. A lot of people, when you say the word script, they think, that's kind of throwaway. Real developers don't use scripting languages. You'll kind of hear that mindset. Instead, they write hundreds and hundreds of lines of Java code or whatever. But the beauty part about this is, I can very quickly read this, and once I know the API, and it's got a few little idiosyncrasies, and know the kind of concepts that go back to functional programming of like mapping and filtering and flat mapping and what all those mean. And I'll explain flat mapping in a little bit if you don't know what it means. But basically, I'm going to load some tab-separated data. I'm going to split it into words. This would be like the contents of my Wikipedia pages. And I'm going to spit out some new tuples, and you can write tuples literally with parentheses in Scala. It'll have a word and the ID, so I've already done a flip right there. I came in with an ID and then text. Now it's word and ID. And then the last steps where I do group by is where I bring all the common words together and do final counts to get the inverted index and the count on each document. Actually, I forgot. I'm actually not doing the counts here. When we see the Spark example, it's actually a little more complicated than this. Complicated's a good word. Only because it's actually adding the ability to count the words occurrences per document, which again is what you really want. So this is slightly simplified, but I think it gives you the sense that knowing this API or something like it, and there's a Clojure API that's like this too, you can just bang out this stuff really fast. You can experiment. You can play with it. There's a local mode for running things on your laptop and cascading. This is where we want to get to as far as the kind of non-SQL-like data processing that we like to do. But it didn't solve all our problems, and one of them was that MapReduce was only ever designed for doing batch mode processing. And when you hear that word in the big data, or at least the Hadoop context, it always means I've already got the data parked somewhere, some massive file system, and I want to just ingest it all or some big subset of it and do a big batch of processing, not live, not real time, and so forth, as opposed to streaming, where I have data coming in and I want to analyze it as quickly as possible. And actually, my favorite example of why streaming is important and growing important is actually this one we just talked about, inverted index. In part because that's something you can certainly do in batch mode, and that's obviously the way that the search engines used to do it. But it's definitely a competitive advantage if somebody makes an edit on their web page and a web crawler hits it, say within 20 minutes or something. You'd really like that change to show up immediately in your search index and not 3 hours from now or tonight when you run your batch job. So streaming even makes sense for things that we don't think of so much as streams, like this data set. But it also makes sense for things like I'm monitoring the Twitter fire hose, I'm monitoring my log files for signs of anomalies in the system, that kind of stuff. So we need streaming. And the performance needs to be a lot better. Once again, it was fine at the beginning when things were crude to throw more hardware at the problem. We all want to save power. We all want to optimize our resources, so we need better performance. And that's where Spark comes in. So about 2 years ago, 2013, Cloudera, the big Hadoop vendor, said, we've kind of reached a point where MapReduce really has gone as far as we can take it. This Spark tool has been incubating for a while, first at Berkeley and then as an open source Apache project. We think that's kind of the future for what the compute engine underneath everything ought to be in Hadoop. So they embraced it and sort of put it on a rocket ship. It's now maybe the most active open source project in the world. I believe it definitely is on GitHub and Apache, but maybe not for Linux or compared to Linux or something. So what does it give us? Well, as we'll see in a minute, it does give us very concise APIs that expose the kind of abstractions we need for composing data flows, whether they're sort of traditional SQL, and there's even a SQL dialect you can use for this, which we'll see, or I want to do something that's maybe non-trivial, like an ETL process where I'm going to do various staging and validation and transformation and splitting streams and so forth, the sort of things that you wouldn't really think of doing with a SQL query so much. And it actually supports 4 APIs right now. The R one is actually coming in a future release, but it's basically ready. But Python, Scala, and Java. This actually made it possible. In fact, a recent change in the API finally made it possible for the Python code to be just as fast as the Scala and Java code. So it's completely no longer necessary for the data science guys to throw their code over the wall to some engineers to port it to Java or Scala. Now, of course, there's always still the usual issues about deploying something to production, testing it before it gets there, the usual software engineering challenges that we all know we have to address. So I don't want to minimize those kind of aspects, but it's not necessary anymore to simply port things over to what is perceived as the real systems language like it used to be. And it actually has a SQL dialect, so we can actually write SQL queries even interactively when that's the right way to work with the data. So we do have this interactive shell. It's basically the Scala shell, and it gives us, it doesn't give us Java, but we can write in these three languages, and we can also write SQL queries. Well, in fact, the example I'll show in a little bit, I'll embed SQL queries in a larger Scala program, but there's even a variant of the shell that just brings up a SQL prompt. So you just write SQL queries like you would with Hive or any of the database tools that you've ever used, which is really, really good for I've even worked with product managers, people that are not technical at all that know how to write SQL queries because they've just learned how to do this as part of their jobs. And enabling those folks to just log into your Hadoop cluster and write SQL queries is pretty powerful. And do it at reasonably good speed, not the slow speed that MapReduce forced on you with Hive. And because of these composable primitives that I mentioned, it's really easy to implement a wide class of algorithms, and you get reasonably good performance, so you can do even iterative algorithms like graph traversals, like training a model in machine learning and that sort of thing. It used to be that these were very hard to do with MapReduce, and you'd have to either work around the system or tolerate poor performance, but now we can do that a lot better. Some other really interesting things they do. MapReduce never actually knew what the long sequence of jobs were that you wrote were trying to accomplish. It had no visibility into the pipeline. It just knew about the map step and reduce step that might be, say, in any of these sort of coarse-grained steps. Here, Spark actually builds up a lazy directed acyclic graph of the computation, and it can do things like squash some of them together in the same JVM process. So you can conceptually write things separately, but get the optimization of having things rolled together. This also benefits data recovery. So in fact, if you lose like a partition of data, Spark can go back to wherever the last checkpoint or data source was and reconstruct that partition, because it understands the lineage of all the data, because it has this directed acyclic graph in memory. And I actually mentioned this already. There's a new DataFrame API that's inspired by Python and R DataFrame concepts that raises the abstraction level even a little farther than the core of Spark, but also enables query optimizations and the ability to use any of these 4 languages I mentioned, including, actually 5, including SQL, and still get the same performance, which I think is a huge step forward. And because of its ability to be fairly efficient, Spark can actually support a streaming model, which is basically a mini-batch model. So Spark actually evolved also as a batch mode system like MapReduce. It started, it was about 2008, 2009. But because of its relative efficiency, they realized that they could actually support sort of the 80-20 solution to what most people mean when they really mean streaming, which is, I just need to process the data fairly quickly. It doesn't have to be per event or instantaneous, like milliseconds. Like my inverted index example, where, yeah, I don't have to respond to a user immediately when the index is updated, but sure, it'd be great if I could do it within a minute or whatever. So they invented this mini-batch process called, well, I actually have a slide, on the next slide will show it a little bit. 2 other important benefits, though. One is that because it's a mini-batch, you actually can just repurpose the same code you've written for your batch jobs inside a stream processing system. And if you ever use the Lambda architecture, for example, this really solves a huge problem that is typical of the Lambda architecture, which is, in other tools, you often find yourself re-implementing the same logic twice, once in your streaming tool like Storm, let's say, and once in your batch tool like MapReduce. So now you don't have to do that even. You can just write one core code base and then repurpose it for those 2 different scenarios. And in addition to reusing batch code, you get the ability to do window functions. So conceptually, it looks something like this. Each of these blue boxes is a resilient distributed data set. That's the distributed collection that's behind the scenes, always holding your data. It's resilient in the sense that if a partition is lost, like I said, it can go back and reconstruct it. It's distributed in that the data will be partitioned across your cluster so that you get the benefits of the parallelism. And in the case of a streaming process, they use something called a discretized stream or D-stream, where each time window, and this is something you specify, down to about a second is the minimum resolution. It's going to put that batch of data into an RDD and let you process on it, or even do things over windows of them. So if you're like computing moving averages, or what are the most frequent tweets or whatever, you can do it this way. Okay. Now I am going to show some Scala code, even though this is data science talk, and I'm going to use as my source for the permission to do this, Vitaly Gordon. This actually is a link to a talk he gave at Scala Days, but it was convenient that he talked before. He often advocates using Scala, and especially in this sort of pre-Spark 1.3 mode where you didn't have the ability to run Python at the same performance as Java code. So I'll just use Scala, and mostly because that's the only thing I know how to do anymore. So anyway, let's actually look at the inverted index. And I assume that you don't know Scala. How many of you have actually used Scala? Just out of curiosity. Oh, well, all right, more than I thought. The purpose isn't really to teach you Scala, of course, but to give you a sense of what it's like to create a data flow of processing data in a language or toolkit that gives you the right functional abstractions, namely immutable data, operators I string together to get from A to B with making all the little micro steps that I need to make. The Python API is almost identical. It's amazing how similar Python code looks to this. In fact, I'll show an example of that in a second. The Java code isn't quite as concise, but now because of Java 8, you can do things like embed anonymous functions, which is very important for code concision. So anyway, you start always with importing stuff, whether it's Java or Scala, the same idea. And then Scala lets you declare singleton objects, and that's what you would put your main routines in. So that's what I'm doing here to calculate the inverted index. Obviously, that's my entry point when this thing runs. You always start a Spark program by creating a Spark context. That's your entry point. The first argument actually is the cluster I'm talking to. In this case, I'm just talking to my laptop, so it's just local mode. And there's various ways you can construct these things. But now let's actually start processing this data. So the first thing I'm going to do is assume that my crawl data is just in text files, so I'm going to load that. And again, actually, this could be a directory of terabytes of data, but it will figure out how many tasks to spawn for me. And the first thing I want to do, and we're a little cut off at the top, but I think you can still see it, I want to map over each line. And so this is an anonymous function I'm passing to the map method, and you can use curly braces instead of parentheses for function arguments because it gives you this nice block structure. And also, actually, while I think of it, notice there are dots at the beginning of these red things. The red things are always methods because that does the real work. This is actually one giant expression where I'm just building up a pipeline. You could certainly have intermediate variables for each of these stages, but when I'm just doing it all at once, I don't like to declare variables where I have to come up with a name. Anyway, so I'm going to split the line on tabs and then return a tuple containing the first element and the second element. No, I'm actually splitting into two elements. That's what the 2 is for, because obviously text could have tabs in it, and I don't want to treat those as fields. So now I have a tuple of my document ID and the contents of my document, one record per line. Flat map is basically like map, but instead of being one-to-one, it's zero-to-many outputs. So here what I'm doing is taking each line and splitting the text into words, and then outputting another tuple, which will be the word, which I've now put in key position. By default, it uses the first field as the key, and then the path, because I need to keep track of where this word was found. And I'm using flat map because obviously I'll get many of these per line, and flat map will just automatically compress that nested collection of words per document into one giant collection of word path pairs. And that's, of course, what we want. This is my favorite little bit of code. This is kind of a classic Spark idiom for counting. I'm taking those tuples, and I'm going to still use the word and path tuple as a key. So it will be nested inside a larger tuple that has a seed count of 1 for each tuple. And then the next step, reduced by key, is an optimization in Spark where it's basically group by over all of those word path keys, and then it just sums up the counts by whatever function I pass it. So I'm just going to grab the two counts, N1 and N2, sum them up, and I'll end up with data like in that gray box where now I'll have unique word path pairs and then some count that's one or more for each word. All this thing does is it rearranges the print. You know what I love about this line? This would be like nasty Java. It'd be like 5 or 6 or 10 lines of Java code. All I want to do is get back to using the word as the key. So I just shifted the parentheses of these tuples and the nested tuples so that now I have word as the key and then path and count as the value. And that's why I just love about this. The reason the word case is here, this is actually a pattern match idiom in Scala. It lets me reach in and tear the tuple apart just without having to, like call get element kind of stuff. So I'm pattern matching on that nested word path tuple, the original key, and count, and then creating a new tuple with the word as the key and then path and n as the count, as the value of the tuple. Now we do a traditional group by over the key, and then this last bit, all it's really doing is formatting the output and on the fly sorting by count descending. So that's where it says sort by, and then I have another pattern match. All I'm really doing is saying, all right, when you're doing this sorting, treat the count as negative so it'll actually be descending, and do a secondary sort on the path. Actually not necessary, but it's useful for unit testing. And then I'll just make a string out of those, and then save all of this to a text file, and then stop when we're done. Everything except that stop at the bottom and the initial input through text files, I could take that code, put it in a library, and do it in batch or streaming on the fly if I wanted to. So I get that reuse. So anyway, whether you understood all those details, I hope you got the sense of how an API that exposes the right abstractions, in this case, designed for data, really lets us crank this out quickly. I wrote this in 30 minutes the first time I wrote this thing. Now it's evolved a lot since. But it was because I understood those abstractions and I wasn't thinking about really, really low-level gritty details that MapReduce would force on me. And I was able to crank this out quickly. And this is a 12-point font, I think. So you can actually almost read the whole thing. Maybe those of you in the front can. OK. Well, once again, amazing combinators. That's sort of a functional programming term. I'm one of those uppity guys in the top hat. Anyway, operators is a better word, really. But that's why I use the red, even though it sort of fades out on this projector, because those are doing the real work. Those are the heavy lifters. And I just tell them, OK, when you reduce by key, what are you reducing by? When you're mapping, all right, how do I want you to map these tuples and so forth? So let's look at the slightly broader aspect of the Spark ecosystem as a sub-ecosystem of Hadoop, or you can actually run Spark outside of Hadoop on Mesos or even as a standalone cluster. Shameless plug, Typesafe is offering commercial support for those latter two options. So talk to me afterwards if you want to give me your money. All right, we can write SQL queries. So let's look at that. First of all, very important for a lot of people who, in a mature Hadoop ecosystem is they've already got a lot of stuff in Hive. They've been using Hive tables forever. Spark can interoperate with Hive, so you can get faster queries, or you can. So my favorite example of this actually is use Spark for that ETL cleanup, munging process, and then just write Hive tables. And then your data analysts, as soon as that process is finished, they can go write their queries to see, what's the latest tweets or whatever. It has an internal query optimizer called Catalyst. So basically the last two lines, you have two options. You can either write real SQL, or you can use this new DataFrame API, which is sort of like a builder pattern for expressing the queries in a more type-safe way as opposed to embedded strings, which actually is the preferred way today. So let's actually see an example of how you might use this with Hive. And if you wanted to use Spark's own SQL dialect, the code would be almost the same, but it's not quite as mature or as feature complete as the Hive version. So this is still really popular. So there's some stuff that got cut off, and just an import statement that doesn't really matter. Create a Spark context as before. Wrap that in a Hive context, or use a SQL context if I'm not talking to Hive. And then I can basically write the same kind of queries we saw earlier. I can create a table. I have this SQL method, and I have to pass strings. So the downside is it's not type checked until runtime. But that's OK if this is actually an interactive shell where I can tell right away if I messed it up and redo it. I can load data. This is classic Hive for just loading data that I have stored in my local file system into HDFS. And then I can start writing queries. The /show method is just a data frame method that's convenient for seeing the first 10 records and to see what you've got. So when I did this, what did I do? Is it off the screen? Actually, when I do these queries, they return something called a data frame, which has this higher level abstraction for SQL awareness, schema awareness of the data. And then I can actually use this in the regular Spark API if I want to take the results of this query and then do some munging on it and create a new Hive table or whatever. It's just all integrated right there. And if you don't like the nested query strings, well, there's this alternative that we'll see in just a second. So it turns out actually when you do this either in Python or Scala, most of your code is going to look really similar. All you'll do in this particular example I showed you, which is even a trivial change, is you replace one statement. The import is replaced with a from PySpark SQL import Hive context, and then you just delete the val keywords from the Spark, the code I just showed you. Actually, were there any? I guess there were at the beginning for the Spark context, and then the code is actually Python code. So that's really nice. In a way, that's great too, because it means that if you know Python and somebody gives you a Scala example to look over, you can probably figure out what it's doing pretty easily. So let's look at the alternative, which is the DataFrame API. I'll basically do kind of the same code. This will be more type-safe because it'll be doing checking at compile time, and that is an advantage. The disadvantage for anybody who already knows SQL is they have to kind of learn this DSL, as opposed to just writing with the language they already know. But it starts off the same. We create this Spark context, and this time I'm going to use the SQL context and not deal with Hive at all. I'm going to load some data, and by default, it uses Parquet, which is sort of the hotness in terms of data formats in the Hadoop file system. It's a column-oriented storage. It actually compresses columns, does some other nice things that are pretty handy. This was something Twitter helped develop, actually. But you can load JSON, and it can parse JSON on the fly for you and infer the schema. You can certainly use some other file formats that are popular, including text, even though Martin and Todd convinced us never to use text again for the rest of our natural lives. So maybe I want to, actually the WC, this is supposed to be like a word count data, or just think of it as inverted index. And maybe I want to see the counts descending. I want to see the most frequently occurring words. I can just do data frame, order by, and then this funky little syntax with the $. That's one of several ways you can express. I want you to find the count column in this data and sort it descending. So it's a bit idiomatic Scala that they had to use for this particular API, but you get used to it really fast. And then I can see the first 10 very easily just to make sure it looks sensible. And then cache is an optimization Spark exposes to you to say, I'm going to keep going over this data over and over, so cache it in memory if you can, so that you don't just recompute the whole graph every time. Otherwise, it would actually go back to and reload the data every time, which is going to be inefficient. I could do things like, show me all the words that are longer than 20 characters. Again, using that idiomatic syntax. This time I'm passing a predicate as an argument to filter. And then I could save the results back to Parquet if I wanted. Actually, so I put in the extension just to show that it's Parquet, but it doesn't matter. It's going to write by default Parquet and read Parquet. I just use that as a naming convention here. So very simple. Actually, I guess it's not quite like the previous example. But if you prefer working in an API that's type checked at compile time and also gives you really good performance, it's an excellent tool. So what about machine learning and graph processing? Let's finish up with those. And how am I doing for time? Pretty well. OK. So there's a MLlib, which is part of Spark. It's a rapidly growing library of standard machine learning algorithms. And it's built on this core infrastructure that gives us really good performance for the most part. By the way, I just thought of something. If you want to post questions, post them on the app. And also remember to review the app. I meant to say that when I started. Let's look at a kind of an interesting example. So I mentioned streaming is really hot. Well, a lot of things that we do in machine learning, we've been doing in batch mode. But there's some things we'd really like to be doing in real time. And I use the word real time with air quotes, of course. And one of them is finding clusters in data as it's coming in. The other one they support right now is logistic and linear regression. Yeah, so you can like train models on the fly and do predictions on the fly. The example I'm going to show you is actually from the Spark distribution itself. So you can just download Spark and you'll find this code in there. There's a bunch of messy imports, but mostly what I wanted to show you is I'm importing an example, and I've deleted the org.apache on the front here. That's not legal Scala, but just so it would fit. There's some built-in linear algebra stuff for like representing vectors of features. You know, like a classic example would be like, you know, say I'm rating like housing prices. I might have a vector for the price, number of rooms, those kind of features. And what else here? Then labeled point, if I have data that's already pre-labeled as being part of a certain cluster or grouping, then I'm going to use that to test how accurate this is. So I've done these imports. Now I'm going to import a streaming context. So we'll mix both machine learning and streaming. This also wraps, I think I've got a build here. Let's get through that. So there we go. So I, once again, create a Spark context, create a streaming context. And here the second argument is important. It tells me how many times, or what's the length in some time window that I want to capture data and process it as a mini batch. For various technical reasons that we won't get into, this kind of minimum is really about a second. You don't want to go in, you can't really go below that and have reliable performance. You can go up to really long times if you want. Like if you have very slow streaming in data, you could have several minutes if you want. The only risk there, of course, is that data is going to be sitting in memory and it could get lost. There are some ways that they're adding resilience so you don't get data loss in the event that the job happens to crash while you've got data that's been sitting there ready for the next iteration. We're going to load two data sets, one of which will be the training data that's already labeled. No, it's not labeled. We want to use that as for predicting, but then we're going to have some test data that is labeled that we'll also load. And what we're going to do when we actually start processing is, as the data comes in on the training stream, we're going to train or look for clusters with k-means, and then we're going to take that data and see how well we did at predicting the location of these training sets. So the training data already knows where it should be. We're going to see how close we got to it. So the text file stream means we're going to just listen on a socket for data to come in. Yes, that's correct. There's also like directories. You could watch directories and so forth. We'll treat each record will be like a single line of text. And then this is a classic idiom of just mapping over that data and passing it to some parse method that knows how to tokenize that line of text and turn it into an object like a vector in this case, or a labeled point that's also a vector but also has a label attached to it. And I love this because it's so concise. To actually use streaming k-means, we just instantiate one and we set some properties. Now, all these things in yellow would normally be like command line options so that you can vary them. But just for simplicity, I treated them as constants. So we're going to find, like, say, 5 clusters in the data all the time. The decay factor says, should I remember previous data and mix that in, or should I forget it? And basically, it's a weighting. In this case, 1 actually means forget all previous data, treat each new batch as brand new data and find its clusters. 0 would mean use all data in the past, which is kind of dangerous because obviously you're going to be accumulating data. And then we need to initialize centers, and we're going to assume that the end features is actually the size of our vectors. So let's say we know that we've got 20 features in our vectors that we're going to do predictions with. This is a function in Scala for just transforming a labeled point into a tuple that has the label as the first element and the rest of the features in a vector as the second element. I need that for one of the next functions here. So this is a way you could declare an anonymous function, or actually a named function in Scala. It would look similar in like Python and Java now as well. Now, everything I've done up to this point, in fact, even at this point, nothing's actually happening. I'm building up a pipeline, and it's not until the next line on this, when I say start, that it'll actually run. So, as I said, I'm going to have these 2 streams coming in. I'm going to train on the training data on each batch iteration, and then predict from that data using what came out of the test data with my F function it can extract the fields that I need. And print is just, really it's a debug statement that they have in the API. It'll show you like the first 20 results of this returned RDD, a resilient distributed data set. So normally you wouldn't see that in production. You'd be writing this out to a file or a database or something. And then finally we start it and then wait for it to terminate, which could be forever, hopefully. Okay, the last one I want to talk about, and then we'll wrap up, is graph processing. So this is the idea, and there's an API called GraphX. Well, there's a whole bunch of these in the real world. Vitaly talked about some actually at LinkedIn, your social network, your Twitter followers. Epidemics are an interesting case. The interwebs, they form a graph. I did not misspell TEH, actually. But it used to be that distributed graph processing was actually sort of a research problem, and we didn't know how to do it well. So most people just sort of hand-coded specialized versions of whatever algorithm they were trying to compute using MapReduce or whatever. But now we actually have the ability to build more general-purpose graph engines that can be distributed. In this case, they're built on top of Spark. Quickly, I'll go through the code. A lot of it is just set up, but I wanted to give you a complete example. So the first thing is a bunch of imports again, and we'll not even say any more about that. I want to do 20 partitions, again, of something I would actually make a config option. There's several ways I could partition the data. Actually, in this case, we're going to actually duplicate some of the vertices. Whenever an edge is going to cross a partition, I think I got this right. Actually, we want vertices to be clustered together more than edges, so we'll actually be duplicating vertices instead of just splitting edges, is this particular model. And these next two values, too fast. These next two ones are just like, try to save everything in memory as we're processing. And then the tolerance, we're actually going to do PageRank, because I didn't really say that yet. We're going to do PageRank, so when we iterate on computing the weights of our nodes in our social graph or whatever, we'll wait until we get a tolerance down to 0.001, and that'll be the end of the iteration. So it'll just run to completion with this tolerance. And then somewhere we're going to get the data. That'll be our input. Okay, so this is the real meat of it. Once again, Spark context, create that. Use a static method edge list file where we give it the Spark context, our input, and then those other values we just set that tells it how many partitions and so forth. And then cache that in memory is the last step here. That's actually, the first step here will be to give us unpartitioned graph data. Once again, I'm setting up a pipeline. I haven't done anything yet. This fold left will be used to take that unpartitioned data and partition it by the partitioner that I told it to use somewhere. Actually, where did I tell it? Anyway, it's somewhere in here. Maybe I left it out. And then the last thing we'll do is actually print out how many nodes and edges we have in this graph. And then finally, we can just run PageRank with one line of code, cache the vertices because we're going to keep going over those. This last step then just computes the total rank. It sums up all of the ranks of the individual nodes. Just a little bit of Scala-isms here for that. And then finally, we can just save this as tab-delimited data back to text files and then stop. So once again, actually most of this is set up in Teardown. There's just like maybe 10 lines of code that do all the real work. And the rest of this is like configuration and input and output. I think that's my last example. It is. I want to mention a couple of other things that you should watch if you're a data scientist. One of them we're going to get a talk on. I think it's the next one, actually. Arno is going to talk about H2O, which is a really amazing in-memory compute engine where a Spark can handle not only in-memory but also data that has to be flushed to disk. How many of you looked at the Julia language by chance? So Julia sort of aspires to replace R. It's relatively new, but it's rapidly evolving. It's a really elegant language that you might want to check out. So we have maybe 5 minutes for questions.